Imagine you're solving a puzzle, but instead of using numbers like 1, 2, or 3, you're diving into a special kind of math called finite fields. These are tiny number systems with only a few numbers in them, like a clock that only goes up to 5. Now consider a simple equation like x2 plus y2 equals sine 1. The Weil conjectures are all about predicting how many solutions this equation has in these tiny number systems. Here's the cool part. The number of solutions isn't random, it follows a hidden pattern, and the Weil conjectures are like a treasure map that helps us uncover that pattern. Let's break it down. First up, we have the Zeta function. Andre Weil, a brilliant mathematician, came up with a special formula called the Zeta function. This formula doesn't just tell you how many solutions there are for one tiny number system. It tells you how many solutions there are for all possible tiny number systems at once. It's like having a master key that unlocks every door in a building. Now, Weil made 4 bold predictions about how this Zeta function behaves. 1. Rationality. The formula is a simple fraction, like 1/2 or 3/4. 1. Functional equation. The formula has a kind of symmetry, like a mirror image. 1. Riemann hypothesis. Analog. The numbers in the formula line up in a special way, like soldiers standing in a straight line. 1. Betti numbers. The number of solutions is connected to the shape of the equation when you draw it in higher dimensions, like counting the holes in a donut. Then along came Alexander Grothendieck, another math genius. He built a whole new toolbox called étale cohomology. This toolbox let mathematicians study these equations in a completely new way, linking them to shapes and spaces. It was like discovering a new language to describe the hidden patterns in the equations. In the 1970s, Deligne used Grothendieck's toolbox to prove the last and hardest part of Weil's predictions, the Riemann hypothesis analog. This was like finding the final piece of the puzzle and completing the treasure map. But why does this matter? The Weil conjectures aren't just about solving equations. They show us that math is deeply connected in ways we never imagined. The same patterns that show up in tiny number systems also appear in the shapes of spaces and even in the physics of the universe. This discovery has inspired breakthroughs in cryptography, string theory, and much more. In short, the Weil conjectures are a shining example of how math isn't just about numbers, it's about uncovering the hidden beauty and order in the world around us. So if you enjoyed this dive into the secret world of the Weil conjectures, don't forget to like and subscribe for more mathematical adventures.